It's off. Yes. Okay, so we had about 5 minutes of lecture with the microphone off. Essentially, I distributed some samples showing the recrystallization and the grain growth and cold work copper. If anybody is interested, you can ask me about it at any point in the semester. I have the samples on my desk. And we were moving on to another question that arose after last class with respect to the necking of a tensile specimen. Because I said we're going to form this cone and cup structure, so we have a flat portion, and then on the fracture, when it's completely separated, it's going to look, we have the neck zone, and then we have the 45-degree slope. So this whole thing, in that case, would be the fracture surface. This is just the original surface that's a neck. And I mentioned, so we have the opposite side here when it failed. So this is essentially a little disc in the middle of the sample, and then you have another annulus around it, if it's a round specimen. So the reason why the crack starts here is tension. And you can have the most ductile material you can think of. The way it's going to break is by formation of microvoid, ultimately. So if we're looking in details of what happens here at the initiation is, say I had a little inclusion, which I always do, or even I had a grain boundaries, or I had something that was not regular in my microstructure. So these are anomalies. They're not really defects because you expect them in any industrial material. Thank you very much. You can avoid these if you have whiskers, if you have perfectly made crystals. You can avoid having these sites where the voids will start, and then if you have that condition, you start pulling on it, you don't form the voids, even if you don't put in a hydrostatic tension or compression. So the fact that we're forming this cup here is because we're susceptible of forming microvoids when we pull in tension, because there are always some impurities in the metal. So what happens with the voids, I'm going to draw it as a function of time here. So over time, they'll stretch and stretch, and they become a little wider. And then you get to a condition where they'll touch each other. And there's no material anymore. It's a crack that you just formed. And you have to think about it in 3 dimensions. But when we go back to a fracture surface, and I can show you guys a lot of examples of that, you're going to see it this way as little round things. They're not always round. When you see these, we call them dimples. They are essentially a cut view of this where all the microvoids merge together. So that's probably going to help your intuition as far as what's the effect of pressure now. Because we had that graph last time where I said atmospheric, so you have a big center zone where it goes really flat, and as you keep increasing the external pressure on the specimen, the size of the central portion, I should just use the cursor here. So this, if we start from here to here as the diameter of the central portion, it's going down here, maybe by half. Here, yeah, here it's about half of what it was over here. Keeps going down. Here you have a little bit, and here it's almost going to a single point. That's because you are preventing the formation of the voids by superimposing compression in the whole volume of the specimen. So you get more deformation. So it's just another demonstration that, you know, what we get out of the tensile test at some point starts not having anything to do with the hardening of the material, with how exactly things are happening in it. So even when we form that neck here, there'll be a point where even if we were to monitor the exact net area of that section, we still don't take into account that we're forming voids in it. So it becomes impossible to really characterize it. You just have to understand that it's a completely different process, a micromechanism of forming these microvoids, as opposed to deforming the material with dislocation, multiplication, and then recovery and recrystallization, and also those things that have to do with the bulk of the polycrystal. So this is a little bit of a summary, maybe more details. I'm happy. A lot of this, when we do failure analysis, this is one of the first things we go and look for. Do we have those dimples? It tells us if the material behaved and failed by an overload, or if there was something else related to the environment or corrosion that caused a crack to develop in another way. Because I could have this sample under the pressure and still have it crack very slowly for environmental consideration. And that's something we'll talk about in the second module of the class. So this curve here is essentially just to show, depending if you can start the recrystallization very quickly, you can have your flow stress during forming essentially go through a steady regime right away. But there will be a situation you start rolling and you keep accumulating deformation and deformation, and you try to recover it, but if it takes time to reach to start recrystallization, that's where you have a peak in your curve here. So that's where speed really makes a difference. If you go slower, you're probably going to allow for recrystallization to start, and you won't have that peak in force. The significance of the peak in force is it will make the deformation less homogeneous, and it's a situation where you could have tension in a forging, for example. So you have to keep track of and trying to optimize your flow stress. So a material that's going to go through these transition is something to be careful about, and maybe try to avoid it depending on the situation. All right. So today there's the tube fabrication. You had a question about tube fabrication that was really good, and I mushed it. So we're going to go through that in more details, because I can see that as being interesting. And, you know, if I talk to my younger brother, he will also ask, like, how do you make these things? Well, the cheapest way to make a tube is to start with a sheet, fold it, and put a seam well. It's very hard to beat in terms of price. It doesn't necessarily give you the best properties. For steel, you tend to get pretty good mechanical properties. So that's what's done for a lot of fire sprinkler lines. You can do them with just electro-welded sheets. So you have your sheet, and you find your way to make it all around. And then you apply a very high voltage. It's a resistance weld, electro-resistant weld, and you make that seam over there. One issue with these electro-welded seams is you always, because you're introducing a weld, you're going to have residual stresses, and you're going to have some variations in chemistry. This becomes a casting in that little area. So we've seen in practice a lot of situations where you'll form pits only at this location. So if I have a pipe that's carrying a gas, and there's a little bit of a liquid in the bottom, and then there's air, this is the perfect sites to start the formation of either crevice corrosion or pitting. And that's why a lot of specifications will call for seamless. So it means that you have to go now through deformation processing to make that tube in a more complex way. Now, I'm going to show you a few examples of doing that. Here, you use a mandrel. So the only way you can do it just with dies is if you can repair, make a friction weld after the fact. So you form that shape, go through the die, and then repair it, make it seal again. But that's a weld. So we're going to take that one out. So with a mandrel, one way is to limit your length. So you come with a piece that is hollow, you insert it in the assembly, and you have the mandrel. If we look at, let's look at a side view here. So you have the mandrel on the inside. Well, this is drawing, but extrusion would be the same in the other way. So you have to keep this in place and you have to have the tube travel through both of them. And you have to control the speed. Here they have the internal mandrel or plug they call for drawing is being hauled. Here it's just floating. So there are different ways to do it, but now you're not so much of a continuous process anymore. The previous image that I wanted to show you, and these are the handouts. Over here, this you can make thousands and thousands of feet of that relatively complex tubing. The tubing is something used for radiant heat. I'm sure there are people coming from different parts of the country here, so some people will appreciate radiant heat that you put into floors. You circulate hot water, and it essentially heats up the whole concrete slab or the driveway, whatever you want to optimize here. In Minnesota, I know it's kind of popular to have those in your driveway, so when you get home, you don't have to plow or anything. There you go. 1, 2. Got the right amount. Okay, so I thought it would show better, but hey, let's see here. Yeah. It's not that good. So if you put water into the, well, first of all, so the pipe is being shown here as the inner layer, an adhesive. You have an aluminum foil or pipe, if you will, some more adhesive, and then another plastic. The plastic is PEX. It's fairly common in plumbing, residential, condominium. It's very cheap. It's flexible, so it allows you to go around the building and make turns without putting joints all the time. And that's the main cost savings. That you have to make, you know, a little more complex or different types of fittings to hold everything together, and that's part of what we are working on right now. This project is relatively old. About 5 years ago, I was essentially looking at why these things wouldn't last quite as long as just a regular PEX tubing. The reason why it looks so complex, there are two main reasons for putting the aluminum there as opposed to just making a straight PEX pipe. One of them is oxygen barrier. So if you have just the PEX, you essentially have oxygen from the ambient air penetrating into the wall of that tubing and essentially being circulated all the way to your boiler. Because the idea here is to be able to run what we call a closed loop boiler. A closed loop boiler doesn't have any oxygen supply, and that's why it doesn't corrode all the way through in a short period of time. If you have any oxygen pickup in a regular boiler, it will corrode right through very quickly. So essentially the idea is you have enough steel that whatever aluminum gets there in the first place, when you throw the original water in, there'll be some corrosion and then it stops. So when they started using PEX, they had the issues of continuing to have new oxygen coming in, and they added that aluminum layer that was really thin but sufficient to slow down or almost eliminate the oxygen transport through the tubing. So they found out doing this that it also brings more memory effect to the tubing. I should have brought some pieces, but the advantage of this tubing is you can bend it and it will keep the shape because the aluminum deforms plastically and impose it will build in the new geometry. It's formable. The regular PEX, you bend it, but it's elastic, so it's going to come back on you every single time. So for making, what happens if you're in the slab, you're going to go and want to do this shape so you have more coverage, and then you tie it back to another loop, under the other, you see you have some reinforcement going, and there's so much going on. You want to be able to make these shapes out of the tube and have them hold easily, so you need much less clamping if when you make a bend it actually holds. So people really liked it. So it was used quite a bit by the builders. The biggest issue that they didn't take into account is because people liked it so much, they started using it for regular potable water. If you do that with the regular potable water, you always have oxygen coming in from the inside. And that's not something that the chemist and the materials engineer thought about, so they didn't make the interior pecs resistant enough to avoid the oxidation over time. The polyethylene is unique in the sense, as opposed to PVC, it needs antioxidants in its base formula to resist oxidation. So depending how much you expect oxidation in service, you have to include more or less of that antioxidant package. It's a little bit like red wine. It's going to be really good, really good, really good, until all of a sudden it goes bad. And that's what we were saying with that system. So anyway, it's kind of like how I ended up learning about this process. But the process itself, I thought was interesting in our context of extrusion, because this is all extruded, but they make thousands and thousands of feet at the time. And do I have, I'm not sure I have the best schematic to show how they were doing it. Yeah, it was proprietary stuff, so I didn't keep the original file. So it's extrusion of plastic this time. It's the very same concept, and it's leading to our overall geometry. So they had, we'll do the aluminum, and I think you guys can figure out the other stuff by thinking about it. So if you have a roll of aluminum here that you supply to the machine, you can make this round. There's actually a lap here. It wasn't like the best quality fabrication. It's so thin that it's easier to have a lap and then do the resistance welding across it. But the idea is you start flat and you roll it and you make it into the shape. As you do this, on one side you insert the inner pecs as a feedstock, and on the other side you bring the outer spec. So when we were talking about mandrel and stuff, if this is coming from the top and wrapping around the mandrel is stationary. So I'm going to put the mandrel here with what we want for the ID. Bring the tubing, have it form around this ID here, keep pushing to provide the pecs on the inside, and then you push to get the pecs on the outside. It all comes out at the same time. You just have essentially the 3 layers, and there's adhesive also. It's all coming off this relatively small machine here that we see the outside, without having to stop to do sections. It's all about bringing the material around the mandrel and then going to the extrusion. And in the extrusion process, there was some reduction. Obviously, they start with something a little bigger, and they worked it to improve the properties of the pecs in the process. That's all in hot condition, so the pecs is relatively fluid, yet it provides enough resistance that you get about the same thickness around the circumference. And when I say about, there was a certain amount of variation, and if you look at the inner layer, the thickness of the inner layer on one side and on the other, because there's no real control over everything here. It's all being put together in the same assembly. And you don't have the same thickness at this lap joint here. You have more aluminum. So you know this is going to affect the thickness of the inner layer and the outer layer. So the issue was really, in terms of service, what was happening on the inside here. Was this thing protected when you had more oxygen. If you didn't have the oxygen, the systems, you know, are being used and are still being used with success. So even though it looks very complex to be able to build all of this in one sequence, I would say first of all there's a big cost incentive, because if you can get this process running, you just keep producing tubing. When you reach your steady condition, you have all the sensor, you keep working at the speed and it just goes. You're producing tubing on a continuous basis without any, you know, extraordinary manpower. So it's an example that I thought was relatively new. They had this idea. It was patented maybe 25 years ago now. So in the material arena, structural material arena, that's relatively new in terms of a process. But the base principle is applicable to steel. So there will be some steel sold at, well, the majority I heard. I don't know all the details, but it's sold as seamless, while in fact it's being brought as a roll over the mandrel. They go around, they make the weld, and then they deform it. So you lose the weld. When you go in the cross section, you can't see the weld anymore, but at some point it was welded. It's like everything else. At some point the steel was melted. you know, it started out as a casting. So it's a much more productive way than starting to cut things. And if you're doing a small volume of extrusion, you can have to drill through the interior of the tube just for practical reasons, and then start working with the mandrels and making the tube from the outside in. But when you're thinking about making thousands and thousands of feet of it, that's where this process, this optimization becomes useful to you. Yes?
Can they ever stress relief?
You can stress relief, of course. If you're doing this with steel, you're gonna want your steel to be hot. So it will relieve a lot of the stresses just by itself as you're going through it. You'll have recovery, and you try to have recrystallization if we're talking about making a steel by this method over a mandrel. And the higher temperature you go, the more you eliminate that casting structure in the weld as well. So, any other questions with extrusion? It was kind of meant to be a wrap-up from the last lecture, but it ended up going into a lot of more details. Okay, so phase transformation. This is something that right away, in the first lecture, I started talking to you about, you know, forming crystals, solidifying. Not everything's going to happen at the same temperature. I said that even if you go with the phase diagram, this is a portion of a phase diagram of copper and nickel. So they're fully miscible. This phase here is the same. You can see it's alpha on one side and it's alpha on the other side. So it's the same crystal structure. What happens is there'd be still a range of temperature for the solidification, because if you go to pure copper is going to melt at a lower temperature than the pure nickel. So somewhere between those two, it's going to be an intermediate temperature. And if you at that intermediate temperature, here we have 35% of nickel, we start to solidify here. So it's going to be a lot more nickel, 46% nickel, and the rest will stay as a liquid. And these numbers keep changing all the way to the last time that you solidify, you only going to have 24% nickel. So from 46 to 24, there's one part that, you know, in the interest of providing an overview, I didn't mention is if you were to do it slow enough, because the reason I'm going back to it is the phase diagram can't always be right. It's just a question of whether you really have the conditions for that to happen. What you need, if you want to end up at E with the same composition, 35% nickel everywhere, you need the higher concentration of nickel to diffuse back into the new solids that are being formed. And that's the part that's fairly unrealistic. at ambient temperature. So at those temperature we're dealing at here for the solidification. So what's going to happen, generally there'll be some diffusion in the liquid, but in the crystal, the first piece that's formed as 43 here will stay at 43 in the cooling process. But I'm essentially telling you that you could trust the phase diagram if you were willing to wait until everything comes back to the same temperature. And in practice, what we can do with this is cool it faster, have a different concentration, and then you heat it up again and have it mix and come back, and that's the homogenization process that we talked about. So it leads to the same thing, but it's just a better explanation of what we were talking about, why we have differences. The example with difference here is just essentially the same phase diagram, except that the higher concentration nickel stays a higher concentration, and it's really what happens in the majority of the practical applications. Now that we know the phase diagram, say, okay, we're transforming. We talked about that you need a nucleation. If you didn't have any mold or anything for your material to grab on, it wouldn't solidify. So there was a question after last class about putting a coating, zinc for example, on the mold, or doing all sorts of little modification to the mold. And I talked about roughness to try to improve the nucleation, to have as many crystals as we can possibly can. I wanted to go back essentially to call on a very fundamental phenomena. So here we have a force equilibrium at that at that point here of the interface. So we're showing three vectors for the surface tension. It's the surface tension between the solid and, say, the mold, between the liquid and the mold, and then we have between the solid and the liquid. That's the red vector. So what happens is, at any point in time, this little corner should be in equilibrium, because if it isn't, it can just move so easily. It's already there. We're not talking about nucleating another element, another phase. We already have a solid and a liquid. If this solid says, you know what, I feel like I should be in better contact with the mold, then it's going down here. And that's increasing the size of that nucleation. It's favoring having more of the transformation taking place. So when we talk about paraffin, if you throw a droplet of water on paraffin, what happens is that interface doesn't really wet well, and that's why you're willing to tolerate a very high angle here for that reaction force. So it's all about temperature. So if you can think of even droplets at ambient temperature. If you ever try to solder something, you'll see that at very low temperature, it will essentially form a bubble on top of the parts that you're trying to weld. But if you go to a higher temperature, now all of a sudden you're bringing on more affinity between the elements, and that allows you to spread and make a bond as opposed to just staying as a little droplet. There's a significance of that in any of the processes for forming precipitates, for forming grain growth, for recrystallization. If I start at an interface, so this is essentially a triple point in a grain of your material, and you're trying to come and arrive with a new face, there's going to be this critical angle to tell you whether you're going to grow or shrink. What's the equilibrium? So there's going to be a critical size where you can reach the angle that you are interested in to start forming and growing that process. So you have to have these interfaces. If you already have large grains and your process of nucleation is at the grain boundaries, then you're only going to have so few recrystallization. It's nicer to have finer grains so you can distribute better these nucleations. And that happens again in polymer, where you just come and say, hey, I'm going to put this little inclusion, so I'm going to start a grain, a spherolit we call it, this specific location, and it just keeps growing in all directions from there. So you try to utilize any interface that's existing in your material when you want to form precipitates or draw new grains. So we're going to talk about straightening. This is an example, just a standard extrusion going through a die. It was part of a wing structure. The wings of aircrafts always have a lot of assembly going on because that's where you put the fuel. So you have an outside shell for wind interaction and trying to optimize all the aerodynamic, and then inside you're trying to contain the corrosive explosive fluid. So there's a lot going on. It's a small aircraft. The sad story is you can't easily inspect the inner structure of the wing. You essentially have to take out a lot of rivets, and maybe you've seen it. You know, they have mechanical issues and they come with the drill and start poking holes to look. They have access holes. So this came with a complete fracture, and they wanted to know why. And you'll see a lot of interesting stuff. This is real. They couldn't do much NDT, but you'll see a few holes here that are not round anymore. They are elongated. So in terms of failure sequence, you had to fail some of the small rivets, and the big rivets were still holding on, but now they were loose. So it's just a kind of a sequence of events that lead you to a final failure. It didn't happen right away. But when we discussed non-destructive testing, which I